Today's lesson is on arc length of a plane curve. It'll be our last lesson in BC Calculus. You know, there's times when we want to find the length of a graph on some closed interval from A to B, and in order to estimate the length of the curve, we can divide up the intervals into small subintervals and use the Pythagorean theorem or the distance formula to find the lengths of each chord, which will be the hypotenuse, and add them up. Let's consider this big idea using the function below. So let's say we want to approximate the length of the curve on this parabola on the interval from 0 to 3, and we're going to step up our x values in increments of a half. So if you think about this first segment from here to here as a hypotenuse of a right triangle, then you know that the distance here on the base is going to be a half, and the height here is going to be 4 minus 3.125, so that's going to be 0.875, and the length of that curve from 0 to a half would be found by using the square root of the a squared, which is a half, and the b squared, which is 0.875, and that calculation is going to be 1.00778, and I'm using my Inspire calculator for that. On the interval from 1/2 to 1, we're going to come do the same thing. So this time the difference is going to be this hypotenuse. The leg is still going to be a half, and then we're going to subtract 2.5 from 3.125, and then that length is going to be 1/2 squared plus 0.625 squared, and that calculates to be 80039 behind the decimal. So continuing on in this format, we're going to end up with 0.625, 0.51539. So here you see each increment moving to the right a half of a unit on each time, finding the hypotenuse by using Pythagorean theorem. I found all of these lengths, and those total up to be 4.08895. So the length of that curve, adding up each hypotenuse along each little imaginary triangle, we've discovered the length of that arc as an estimate. So now we are mathematicians and we want to find the exact length of that curve, and this process will lead us to making smaller intervals by taking the limit of the sums of the lengths of the line segments. And you're hearing that definite integral again, right? So let's put a few restrictions on our functions. In order to guarantee that the integral exists, we have to suppose that first of all, our function is a smooth function on a closed interval. And to be able to find the arc length exactly of the curve over that interval, the arc length has to begin with an ordered pair and end with an ordered pair, and it's got to be smooth on the interval. If it has a derivative, that's continuous throughout the interval. So those are going to be our conditions. So let's take a look and derive the formula to find the lengths of the plane curve between the 2 points. So give me a minute to draw a picture here. So here I've got our smooth curve starting at point A, that's my A, f of A, and ending at my point B, that's B, f of B, and I've taken this little segment from right here to here, and I'm going to think about the derivative of that. So if you zoom in on that, you've got the derivative with respect to x, so that's my leg squared, and the derivative with respect to y, that's the taller leg squared, and that's going to be the length of the hypotenuse squared, which tells us that we can find the length of that little segment by doing exactly what we did on the first example, using the Pythagorean theorem, or the distance formula as it was. So we have L is the arc length, and the arc length is the integral of the hypotenuse dl. So capital L is the integral for the hypotenuse, which is dx quantity squared plus dy quantity squared. Let's factor out the delta x quantity squared from our integral. So we have the square root of 1, and then I'm going to divide the dy by the dx squared and factor out the dx squared. So here we're factoring out the change in x, and then taking the square root of the change in x, that's going to get us dx outside. So the arc length is the definite integral from a to b, and we have 1 plus dy dx quantity squared, and then the square root of the dx squared is our differential dx. So we could simplify down to there, and then recognize that dy dx is the derivative. So the arc length from a to b is the square root of 1 plus f prime of x quantity squared dx. So here is our formula we're going to use. And what we're doing is we're taking the limit as the change in x goes to 0 and the change in y goes to 0 of that original distance formula. Okay, so we have used that to prove. Now that was the reason why we set the restrictions, that the curve had to be smooth, the limit had to exist, and the function was smooth on the interval if it has a derivative f prime that is continuous throughout the interval. So those are our conditions. And if we're finding a differentiable function for y in terms of x, we're going to use this formula on the x-axis values. And if we have a function solve for x in terms of y that's differentiable, we're going to be using y values from c to d and the derivative with respect to y. So just be aware of those. So here we're going to find the length of the curve for this crazy function. I would recommend you put that into your calculator. And then we want to find the derivative, first of all. So we want f prime of x is going to be 4 square roots of 2 divided by 3 times 3 over 2 x to the 1/2 power, which is going to come down to be, let's see, 2 square roots of 2 to the times x to the 1/2 power, so the x can be under the radical here. So here's my derivative, and we want the arc length from 0 to 1, so we want the definite integral from 0 to 1, and the formula was 1 plus f prime squared under the radical dx. So our integral from 0 to 1 is going to be 1 plus, let's see, 2, that's 8x dx. In this case, we're going to need to use some u substitution. So let's allow u to be 1 plus 8x. And du is going to be 8 dx. So we have 1/8 du is equivalent to dx. And then when u is 0, we have 1. And when u is 1, we have 9. So we're ready to integrate, and we have 1/8, and we're changing our bounds from 1 to 9 with u to the half power du, which is 1/8 u to the 3/2 times 2/3, evaluated from 1 to 9, which looks like, let's see, 2 divides 8, that's 4. 4 times 3 is 12. So we got 1/12 u to the 3/2 from 1 to 9, which gives us, let's see, 1/12. And we have 9 to the 3/2 minus 1 to the 3/2. So this is the square root of 9. That's 3. 3 cubed is 27. 27 minus 1 is 26/12. And you can stop at 26/12, or you can continue to simplify to 13/6. So not hard, just be careful. It's a little tedious. This one, find the length of the curve, 2/3 times x squared plus 1 to the 3/2 power from 0 to 3. So we want the derivative, which is 2/3 times 3/2, and x squared plus 1 to the 1/2 power, and then the chain rule on the inside is 2x. So this looks like it simplifies down, and our derivative becomes 2x times x squared plus 1 to the 1/2 power. So our arc length from 0 to 3 is the radical of 1 plus the quantity 2x times x squared plus 1 to the 1/2 power squared dx. And all of that's under our radical. So from 0 to 3, we have 1 plus 4x squared times x squared plus 1 with respect to x. So this becomes, let's see, 4x to the 4th plus 4x squared plus 1 dx. And that looks like a perfect square. So we have the square root of 2x squared plus 1 quantity squared, which is very convenient. So that integral is 2x squared plus 1 from 0 to 3. And integrating, we've got 2x to the 3rd divided by 3 plus x evaluated from 0 to 3. And this is going to be 27 divided by 3 times 2. That's 18 plus 3. And then evaluating at 0, that's still minus 0. So our arc length measure is 21. In example 3, we're going to need our calculator. The derivative is 2/3 times 2/3 x to the negative 1/3. So that derivative is 4/9 x to the negative 1/3. And we're looking from 1 to 8. So the arc length from 1 to 8 is going to be 1 plus 4/9 x to the negative 1/3 squared under the radical dx. So this looks like from 1 to 8, 1 plus 16 over 81 x to the negative 2/3 dx. And using our calculator, we get about that, and they've asked us to round to the nearest thousandth. So tenth, hundredth, thousandth. This is where we're going to truncate 7.289 to meet the conditions of the nearest thousandth. In example 4, we want to find the length of the curve. So this curve is solved for x in terms of y, and our y values are between 2 and 3. So we're looking for x prime in this case, which is 1/2 y squared minus 1/2 y to the negative 2 power. So let's see, we got y squared, so our L, our arc length, goes from 2 to 3, and we have 1 plus y squared over 2 minus 1 over 2y squared, quantity squared. So here I'm just going to expand all of this and find these 3 terms for us to integrate. So the arc length will be from 2 to 3 of this first one plus y to the 4th over 4 minus 1/2 plus 1 over 4 y to the 4th dy. And if we get a common denominator here from 2 to 3, our denominator is going to be 4y to the 4th, and we'll get 4y to the 4th plus y to the 8th minus 2y to the 4th plus 1 under the radical with respect to y. And cleaning that up a little bit, we've got y to the 8th plus 2y to the 4th plus 1 divided by 4y to the 4th with respect to y. And then this is going to be a perfect square. So from 2 to 3, the numerator will be y to the 4th plus 1 quantity squared, and the denominator will be 2y squared squared. That's all under the radical. So the squares cancel the square roots, which again is convenient. So we have y to the 4th plus 1 divided by 2y squared dy. And to integrate that, you would have, let's see, what's this? Y squared divided by 2 plus 1/2 y squared dy, which becomes y cubed over 6 minus 1 over 2y, evaluated from 2 to 3. So this is 27 over 6 and 1 over 6. And then substituting for 2, we've got 8 over 6 and 1 over 4. So this looks like it could be 18 over 6. So I'm considering this is 26 minus that is 18 over 6 minus a negative, so plus 1/4. And if we simplify this down, let's see, we can get 3 1/4. Is that 13 over 4? Yes, this is 3. 6 times 3 is 18, so this is 3 1/4. So 3 1/4 or 13/4. Ooh, that one was very tedious. And I do believe that's the end of our lesson.